Thank you all for coming. My name is JP Walsh, and I am a co-program head for coastal processes here at the Coastal Studies Institute. And today I'm going to talk to you a little bit about some research that we've done looking at sedimentation in different coastal settings. I want to start by just acknowledging students, some other faculty and scientists, and the collaborators. So I've created a big list here. I'm not going to read everybody's names, but something I want to certainly highlight is that students are key to getting a lot of this work done. Lots of man hours are involved. Also at the bottom are a number of sponsors for the research themselves. It is expensive to do this work, and so we write grants to get support to do this research. Just a little bit about myself, for those of you, just to give you a background of who I am. I'm from the Garden State of New Jersey. I have a BA in geology from Colgate University in upstate New York. I have a marine science degree from Stony Brook on Long Island. I have a PhD in geological oceanography from the University of Washington. I did a postdoc at Scripps, and then I've been at ECU for the last 11 years and have been out at CSI for a couple years. So I've been in the state and quite familiar. My history or interest in the coast has really started from when I was a young kid and has grown over time. I also am one of the coordinators for a program called the Semester at the Coast, which is a program for undergraduates, a month-long program. It starts in mid-May, and it's an opportunity for students to live and learn at the coast. It involves doing field work and working in the lab. It gives them real hands-on experience with coastal and marine science. They work here at CSI, and they stay in dorms on Roanoke Island. So if you know anybody that's interested in getting more experience in coastal science, let them know. My research is pretty broad. Today I'm going to be talking about sediment dispersal from land to sea in particular. I also do a lot of work looking at coastal sediment dynamics and how they relate to hazards. We use a lot of different tools for this research, and I'll mention some of them today so you can get an idea. And the research that I've done really stems from river systems all the way down to the deep sea floor, and you'll see that as I go through the talk today. So some of you might not be familiar. The continental margin is sort of the transition zone between land and the ocean. And there's a lot of reasons why we study it. One is it's an important area for natural resources. For example, sand for nourishing beaches or for oil and gas resources. There's also a lot of environmental interests, understanding how ecosystems work, fisheries, and potential resources in that regard, how carbon and nutrients are cycled along our coasts, and where pollutants end up. We also study geologic history to learn about the past and potentially to inform us about the future. And so there's a lot of research that's done in that regard. Obviously, many are concerned about coastal hazards, both erosion and storm surge, and research is related to that. And then lastly, one of the things that you might not think of is national security. For example, the Navy and other federal entities fund a lot of research from a military standpoint. And in fact, my master's and postdoctoral work was funded by the Office of Naval Research. So we use a lot of different tools to study coastal processes, and shown here is a figure that highlights those. So some of the things that we do are to try and understand what's happening in the ocean. We actually deploy instruments to measure the waves and the currents, and you'll see some pictures of those things. We also work from ships and deploy things that use sound to look both at the surface of the ocean, what it's shaped like, as well as look below the seafloor to look at layering in the ocean, as you can see here. And then we also collect cores, where we take different devices and stick them into the seafloor and collect sediments and analyze them. Another thing that I want to highlight is that we use different types of coring techniques and geophysical methods so that we can look at different time scales. And then the last thing I want to mention here is that one of the key tools to understand the past is using isotopes. So what's written here in blue are different isotopes which are used for dating sediments. If you take a core and you bring it back on a ship, and you look at it, all it looks like is basically a big column of mud, and it doesn't really mean that much until you analyze and provide time to that record, which tells us something about sedimentation. Shown here, I'm going to just show you a couple pictures of field work just to see. We do, when we go out on ships, it's expensive to go out on ships. So we work day and night, rain or shine. Here's a picture of us getting wet and muddy off the coast of New Zealand. This is a multi-core device which collects many different cores at one time. Shown here is a picture of Reed Corbett here, who's in the audience, leading a multi-core deployment off of the Roger Revelle, which is one of the large ships in the U.S. fleet. Shown here are a couple pictures. On the left are a couple students that are logging some information for cores that were just brought up on deck. And then on the right is an X-ray system. We use X-rays to basically look at the structure of sediments that are laying down on the seafloor so we can understand something about the type of sedimentation that's occurred. Here's a picture of me working in the Gulf of Mexico right after the Deepwater Horizon oil spill. So certainly some of this work is focused on understanding how humans may have impacted the coast. And then here's a bunch of other pictures just to show we don't just collect small cores, but we do we deploy instruments, as I mentioned, in shallow water bodies or offshore to look at how water and sediments moving around. We use geophysical things to map below the seafloor. We use sort of fancy echo sounders to map the depths of the ocean. And then we sometimes try and take really long cores to look at the longer geological history, and they don't always come up straight. Of course, a lot of the work that we do is not out in the field where it's sunny and fun. A lot of it's sitting in at computers or in the lab dealing with chemistry. Shown here is a graph of something called excess lead-210 versus depth in a sediment core. As I mentioned, we use isotopes to measure sedimentary processes. Lead-210 is a naturally occurring isotope. We go out, we collect a core, and we measure the activity of lead-210 versus depth in sediments. And based on the decrease in the activity and knowing the rate of the decay of the isotope, we can calculate a sediment accumulation rate using this equation here at the bottom. I'm not going to go through the math or the equations. That's the last one of the talk. But I did want you to see that we do use these techniques to understand processes. All right, so today I'm going to talk about a couple different systems where we've done work, just to allow you to understand the differences that we see. I'm going to be focusing on river sediment dispersal, how material from land is being brought into the ocean, and show you how these different systems operate differently. Something to think about is that there's a lot of different factors that affect how much material is coming off the landscape. The precipitation, wind patterns, how far mountains are from coast, how quickly the mountains are rising in response to tectonic processes, how big they are, what type of climate and vegetation, and of course humans have played a big role in affecting some of these sedimentary processes. So that's going to determine how much sediment's coming to the coastline, and then once it reaches the coast, there are many different processes that will affect where it ends up. And so some of the things that are going to influence where material ends up is the shape of the coast, how the geometry of the system, which you'll see in some of the pictures, how variable it is. There's also the waves, the tides, the currents, the rise of and fall in sea level. All those things are going to play a role in where sediments accumulate. So I'm going to start by talking about the Albemarle-Pamlico estuarine system, which is right out our door here. It's the second largest estuarine system in the United States. This is a perspective view from Google Earth. So we're looking kind of west down the state of North Carolina. Here are the Outer Banks. Behind them are Pamlico Sound and Albemarle Sound, which are the two large water bodies, along with a number of smaller sort of parts of the system that make up the large estuarine system. Some of the questions that we're interested in understanding is how much material is actually coming down this system, and how dynamic, how much does it move around, and does it leave the system? So that's what I'm going to be talking about here today. To understand sedimentation in this system, we need to look at what's coming down our river systems. The USGS maintains some gauges that measure the water height or the river flow, as well as sediment transport. And from that, we can calculate sediment loads by rivers. And so if you sum up the four major rivers, the Chowan, Roanoke, the Tar Pamlico, and the Neuse, coming into our estuarine system, the rivers put in an estimated about 1 million tons of sediment per year. And I'm mentioning that number not because it probably means that much to you, but I'm going to compare that to a couple other systems as I talk, as I go through this talk today. In the next couple slides, I'm going to discuss a little bit about the Neuse River estuary, which is kind of a sub-estuary of this larger system. As many of you know, the sounds and estuaries of North Carolina, like most estuaries and sounds, are relatively quiescent compared to the ocean, right? And this is a picture taken from one of the areas on a nice, sort of fall evening with the sun setting. Generally speaking, in the Albemarle Pamlico system, we have tides that are about 10 centimeters, so only about yay big. The waves are typically less than a few feet, less than a meter. Okay, so this is a nice calm day in the estuary. And as many of you know, if you've driven around the Albemarle Pamlico system, it's really big. These are big estuaries, big water bodies. So the river, which comes in at the head over here, the Neuse River, comes in. Shown here is the depth. The color coding represents depth in this figure. So the blues are the deeper waters of about 7 meters depth. And then the reds are shallow water at the shoreline. What you can see just by looking at the map of the system is that it's basically an old river valley. When sea level was lower, the river flowed through here, and this was a floodplain. And as sea level has risen over the last few thousand years, basically it's flooded this area. As a result of this being a large water body and the river coming in at the head, and it being relatively quiescent, sediment sort of comes in and basically accumulates in this system. And it's filled up over time to be a fairly shallow system. It's basically a shallow estuary with a large fetch, which I'll talk about more in a second. So just to give you some data to look at, I'm going to show some cores that were collected in these small tributaries to the estuary, just to show you how sedimentation is occurring in this system. All right, so here's a map. Here's the Neuse River estuary. Here are a couple tributaries. This is Slocum Creek and Hancock Creek, and notice these straddle Cherry Point Marine Air Station. So here are cores going down Slocum Creek and Hancock Creek. And there's a lot of data here. I don't want you to get too overwhelmed, but all these 5 graphs are the same, and they are plots of excess lead-210, which are the black dots, and cesium-137, which are the squares. And what I want you to notice in this figure is that just by the slope of the black dots, which is the decrease in lead-210 versus depth, we can measure the sediment accumulation rates, which are what are listed here in the red numbers. Okay? And notice that at all of these sites, the sediment accumulation rates are a few millimeters per year. They're fractions of a centimeter per year. Okay? Those rates are all about the rate of sea level rise, which is on the order of about 3 millimeters per year in the system. So what you can see is that sea level is basically rising slowly, and this estuarine area is slowly filling up with sediments. In fact, we can use these data to actually look at sort of a pollution history of an area. Shown here are plots of, we measured different metals that are listed here with depth in those cores that I just showed you. And now, rather than showing lead-210 or depth on the y-axis, we can actually show you years, because we know how quickly the sediments have accumulated. So now we're looking at year on the y-axis, on all the y-axes here, and then we're looking at the concentration of how much metals are in the sediments. And what's interesting here is that you can see Slocum Creek had really high enrichment in certain metals in the past. And this was known to have occurred. The Cherry Point Marine Air Station at one point was discharging some not very nice material into this water body, and they eventually basically cleaned up the system. And you can see over time, since then, basically the system is getting better. Although obviously it's still a little bit enriched in some of these metals, but over time it's sort of estuaries are trapping sediment, and sort of there are natural filter for the coast. All right. Now, I've mentioned that estuaries are generally quiescent, but they're not always quiescent. And shown here is a picture of Kitty Hawk Bay during Hurricane Sandy. You can see these are Kitty Hawk Bay is a really small water body. These are big waves propagating across the bay and breaking on the shoreline. These waves cause erosion, and they disturb the seafloor. And so some of the work that we've tried to do is look at how that happens. Shown here are is a figure from cores collected before and after Hurricane Ophelia, which was a number of years ago. Here I'm plotting excess lead-210 and cesium-137 activity versus depth. And we have basically data from two cores plotted. We have data from the blue, which was the core taken before the hurricane, and then data from the red, which is after. And you notice in both data sets, there's a shift in the data. Okay, basically this graph is showing us is that in this area we experienced about 6 centimeters of erosion. There was a lot of material that was basically carved out of the seafloor because of this storm passing over this system. And actually, we were fortunate to have a tripod deployed during this event right at this location. And so I'm going to show you what I have plotted here is some data from the tripod that was sitting on the bottom of the estuary during the hurricane. So in the top panel is wind measured at a local wind gauge. And you can see that the wind was pretty strong out of the north, and then actually got quite strong during the hurricane. Then we've got plotted wave heights. The waves got to be a meter high during sort of as the hurricane approached, and then up to about 1.5 meters. And this is what we call mean significant wave height, which is really quite deep. We're talking about 5-foot waves in water depth that's only about 10 feet deep. You can see how, not surprisingly, the waves and the currents caused resuspension of the seafloor. So you can see this is suspended sediment concentration. So these are how turbid the water, how much sediment's in the water. You see it starts going way up as the waves start feeling the bottom, lifting up sediment on the seafloor. And then in the last panel here is the flux. This is the sediment times the currents to look at how material is moving through the system. And you can see how during this event, lots of sediment was carried upstream initially because during the storm surge, water flooded into the estuary, and then it got kind of pushed out of it to some degree. But there was a lot of sediment moving around is sort of the take-home point of this figure. Now, shown here is another graph or series of graphs of data from cores. So this is cesium-137 activity versus depth. And I don't want you to get too worried about the isotope that I'm talking about. But what you can see in this core is, see this, how the line goes down and creates a bump? And notice how that bump goes up, down, 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 down. The point is that that's an activity profile with depth in the sediment, and you can see it going up and down because there's deposition and erosion on the seafloor. What it's showing us is that in the estuary, even though we think of these estuaries as being fairly quiescent, kind of not a lot happening sort of systems, the seafloor is really quite dynamic, showing centimeters of deposition and erosion over time in response to waves and river input. This is really significant variation in the seafloor, and it's important because if we want to understand things like nutrients and how they're cycled and how organisms that live in these estuaries are impacted, we need to understand how the seabed dynamics relate to the ecosystem. Another thing, this is just using wind information and then calculating how often sediments actually get resuspended in these estuaries. So these are plots of resuspension events versus time, okay? And what you can see is, with time, there's about 50 events of the seafloor getting resuspended every year, which is quite a lot of events. You'll also notice that the occurrence of the events is really quite variable. In summer, we barely have any. It gets hot, and it also gets pretty stagnant in terms of the water in our estuaries, because there's not a lot of fronts that are moving through. Now we're in fall, and if you were out the window, look out the window today, there was a lot of wind blowing. These are when the waves were kicked up and the estuary is getting stirred up again because of the dynamics. Another question that we have is, to what degree, as we mentioned, lots of sediments coming into the system and is probably being stored, but there is potentially some exchange with the open ocean, and this has not really been quantified, and there's some interesting research questions there. Shown here is a satellite image that was taken just after a nor'easter a few years ago, and if you look at the estuaries, you can see they kind of look like chocolate milk, right? And that chocolate, it's not chocolate milk, it's sediment that's in the water column that was created by the wave actions during the nor'easter. And you can actually see sediment plumes coming out of each of the inlets, and some turbid water being advected with the Gulf Stream out into the open ocean. So there's some interesting questions as how what's happening at our coasts in our estuaries might be impacting the open ocean much further away. And so some future work we hope to do is investigating how the connection between the coast and the open ocean. So I've already focused a lot about the river, or I've talked a little bit about the rivers in this area. Another potential source for sediment in our estuarine system is the shoreline. One of the questions we sort of had when we started some of this work a number of years ago is whether or not the shoreline is actually a source for sediment because of erosion, or is it actually a sink because in wetland areas we can accumulate sediment over time. Over the last number of years, we've done a lot of different projects looking at estuarine shoreline erosion, and I'm not even going to try and recap all of that here. But what I just wanted to show you one figure from the Neuse estuary, and what you can see is the hot colors indicate erosion, and the really warm, the oranges and reds, indicate fairly rapid erosion rates of, for example, the red dots are over 1 meter per year of erosion. And this is over 50 years that we're looking at. So there's, along the Neuse River estuary, we have quite a lot of the shoreline is eroding and potentially a source of sediment to the estuary. As you look back in these tributary areas, it's a little bit more variable because the wave energy is not quite as high. But nevertheless, there's a lot of erosion going on in our estuaries, and it's quite significant. Shown here is a figure which you can't see very well, but this is the southern end of Roanoke Island. So literally, if you just flew south of us, you can't quite see it too well, but this is a 2011 image from Google Earth, and overlain on that are maps of, the shorelines from 1947 in red and 2007 in green. And unfortunately, you can't see it very well, but this southern end of Roanoke Island is eroding away really, really quickly. We're looking at, notice the scale here is 500 meters. So we're looking at, in many places, well over 1,000 feet of erosion and loss of whole islands in the span of just 50 years. And this is because we have fairly minimal sediment being supplied, and we have lots of storms with wave action that are acting to erode this system quite quickly. We recently had a PhD student who just finished her PhD, and she's now a faculty at UNCW. As part of her doctoral work, she created what we call a sediment budget, basically an accounting of how much sediment was going in and out. And this was for the Tar River estuary, which is just one of the nooks of the larger Pamlico estuarine system. But you can see in her budget, she's got sediment coming in from the Tar River and sediment from shoreline erosion. And then based on cores, actually measurements of sedimentation, it looks like all the sediment's being stored. So the estuary is a really good sediment trap in this system. Only about 2%, which is essentially within the error, is possibly leaving this system. All right, now I'm going to contrast the Albemarle-Pamlico estuarine system with the Mississippi River dispersal system. This is the largest river in the United States. Historically, it was the 5th largest for sediment input in the world. Shown here, we've got a Google Earth image looking up the Mississippi Valley. And for those of you that don't know, this is the Mississippi Delta, and where a lot of shipping traffic works its way up to New Orleans. And over here is something called the Atchafalaya Delta. If the Mississippi had its way, it would actually divert its course and flow down the Atchafalaya. But because the Army Corps of Engineers is basically mandated to keep this as a major shipping channel, we basically regulate the flow down the Mississippi to continue in this course. Whoops. Whoa. All right, so if we look at a map here of the Mississippi River, it's a huge catchment, about 3 million square kilometers. That's about 200 times the size of the Neuse River catchment. The sediment discharge is about 200 million metric tons today. It's about, which is about 1,000 times of the Neuse River. And the sediment yield is quite high. That just means that it's quite an erosive system. What's interesting about the Mississippi system is that it's, because of human activities, it's changed a lot in terms of how much sediment it carries. About in the year 1700, this is what the sort of natural Mississippi was. It carried about 400 million metric tons of sediment. Because of things like damming, as well as land use change and human alterations of the system, this is what the system looks like today. I should point out that this is sort of a creation. The width of the plot here indicates how much sediment's being carried by different parts of the river system. So this is what's coming out to the Gulf of Mexico, about 400 million metric tons in 1700. Today, you'll notice that the stream looks a lot smaller, meaning it's carrying a lot less sediment to the Gulf of Mexico. But you'll notice some branches have actually grown. The Ohio is actually carrying a lot more sediment. Other branches have shrunk, like the Missouri, because of damming. So there's a lot of detail in this figure. Another interesting change is you can see how the load is being split. We've got a lot of material being carried down the Atchafalaya today and out. And another thing that is quite controversial, or a concern of this system, is that not only do we have sediment being carried by the rivers, but we actually have nutrients because of agricultural activities. This increase of flux of nutrients has potentially expanded the dead zone in the Gulf of Mexico, which is problematic for the ecosystem. Another concern of sediment loss is how the sediment is important for supplying material for the marshes to keep up with sea level rise. And this is a map from the USGS showing land loss over the last several decades and into the future. But you can see there's a lot of red areas on this map. There's a great concern in the Gulf for how do we provide more sediment to these marshes so that they potentially can keep up with sea level rise. So there's a lot of time and money being spent to understand how they can manage this system to add sediment to the lower part of the Mississippi. Anyway, now I'm going to talk about the offshore part of the Mississippi, where we've done a lot of work. This is some data from Reed Corbett, where you can see these are accumulation rates in cores using lead-210. And what you can see is we see big dots near this distributary, which is called Southwest Pass. So we have really high rates of sedimentation here. And as you move away, it basically decreases as you move away. And that's because we're moving away from the source, so the accumulation rate on the seafloor decreases. Work that Reed also did showed how over time, most of this, when sediment comes out in the spring, most of it deposits right near the river mouth. And then in the fall and winter, we have storms that act to sort of disperse that sediment, allowing the accumulation further afield. But something about the Gulf of Mexico system is, generally speaking, the tides are really small, less than about 0.3 meters, and the waves on average are less than 6 feet in the Gulf of Mexico. But every now and again, there are some huge hurricanes where the waves can be over 15 meters, over 45 feet. Significant wave, gigantic waves. In 2005, Hurricane Katrina impacted this area, and Reed and myself and some others put in a proposal to go study how this storm system impacted the Mississippi Delta right here. As you can see, this is Hurricane Katrina passing right over the area we were studying. Right after Katrina, we went out and collected a whole bunch of cores across the shelf. This is the Mississippi Delta and Southwest Pass, and all these dots represent cores. We also collected something called multibeam, which is basically a map of the bathymetry of the seafloor, and I'm going to show you that in the next slide. So here is this sort of postage stamp of a map of the seafloor. Basically, we use a sort of a fancy echo sounder to map out the depths. Red are shallow water, blue is deep. And what you can see is that this is the front of the delta, what we call the delta front. It gets deeper here. This is sediment is piling up here really quickly because it's basically coming out of the river system. And every now and again, it appears that there's actually what we call mud flows, literally mud flowing on the seafloor down this, the front of the Mississippi Delta. Shown here on the right is an elevation difference map. One of the thoughts that we had was that Hurricane Katrina may have been a trigger for mud flows because in 1968, Hurricane Camille caused a mud flow which actually took out an oil rig. So we went out and collected this data and created a difference. And you can see that there's a couple blobs here of significant change which are right on the noses of these mud flows, suggesting that there was reactivation of mud flows along the delta front. In the next slide, I'm going to show you some cores from sites A right here and site B here. What's interesting about A is that A looks just like almost all the other cores that we collected. We basically, again, this is an X-ray of the core, just like you X-ray your arm. What you can see at the upper part of the core is nice layered sedimentary strata. These are layers that were emplaced by, in fact, what we've interpreted to be Hurricane Katrina and Hurricane Rita. And we know that they were emplaced recently because we have short-lived isotopes that tell us that they were recently put down on the seafloor. What's interesting about this other core is it doesn't show any of that layering. What this suggested to us is that after this massive remobilization of sediment on the seafloor by the hurricane, that the seafloor was unstable in this area and led to some mud flow, which was captured by the core that we collected here. One of the reasons why there's a concern about the dynamics of the seabed in this area is that there is a lot of infrastructure on the shelf of, off of Louisiana. Shown here is a map of pipelines and platforms throughout the Louisiana shelf and further offshore. You can see all these blue lines represent pipelines, and all the dots are rigs that look something like this. Okay, there is a massive amount of infrastructure. I'm sure you can understand now when you have a hurricane that comes through that's a Cat 5, why they have to shut down these systems. And it's very typical that when we have a system like we had with Hurricane Katrina, that regardless of our preventative measures, inevitably there are pipelines that are broken. There was something like 540 pipelines that were broken during Hurricane Katrina because of the mobile muds on the seafloor, which can cause some impacts. All right, so based on the map of cores, so shown here is a map of where we collected all the cores, and based on the isotopes, our interpretation of deposition by Hurricane Rita and Katrina. What's kind of interesting is many of us think of Hurricane Katrina as being the big event there, but most of us forget that there was another massive storm that came through right after Hurricane Rita. And if you were a geologist trying to interpret the geologic record, you might think that Hurricane Rita was really the big significant hurricane because, as you can see, these blue bars are found all across the system and are much thicker. And that's probably because Hurricane Rita, when it came through, it cannibalized some of the Katrina deposit and therefore left sort of reduced its impact in the geologic record. Overall, there was massive remobilization, about 5 times the annual sediment that comes in from the river was moved by the hurricane based on our estimates, which is a really substantial disturbance. All right, the last system I want to talk about is the Waipoa in New Zealand. Not a river system you've ever heard of. The reason why I'm going to talk about it is because there was a large National Science Foundation project, or program, I should say, focused on understanding this river system. This system is found on the northeast coast of the North Island. This is, again, a Google Earth image of the northeast coast of the North Island. This is the Waipoua, comes out into this bay, which is, there's a nice pretty picture. It's a very pretty area and a big popular surf spot. The research that we were funded for, actually there was kind of two phases. The first phase was really just kind of to try and understand what type of sedimentation was going on in the system, and I'm going to mention that. And then the second part of the work was kind of looking at how the stratigraphy was being built by floods and storms. And I'm going to kind of quickly go over this just because I'm sure you don't want to hear all the details. Again, here we are. This is the Waipoua on the northeast coast of the North Island. One thing I want to remind you all of that you might not be familiar with is that New Zealand lies at basically at the boundary of two lithospheric plates. There's the Pacific plate here, which is being subducted, basically being forced underneath the Australian plate over here. And that creates volcanism in New Zealand, and it also creates a very complex geological setting. And this river system lies right on the boundary of that complex geological system. So some of you might be, why did we go all the way to New Zealand to study this system? Well, first, what was nice about it is it's a really small river. Okay? It's about 1/10 of the size of the Neuse River. The Neuse River only extends up to about Raleigh. Okay? This is 1/10 of that size. But it puts out 15 megatons, so about 15 million tons of sediment per year, which is about 100 times more than what the Neuse River. So this is kind of like a river of mud flowing to the sea. So it's a great signal of sediment for us to study in the ocean. One of the reasons why the material or why this river is so chock full of sediment is because of this image in the background. You can see we're on a field trip here taking a look at this watershed. This is what we call gully erosion, where because of deforestation and because of the fairly weak sedimentary rocks that make up the catchment, in some areas you have this massive erosion occurring and it's going unchecked because basically once it starts it's really difficult to stop, and so the very high erosion rates in the catchment. Another reason why we were interested in studying the Waipoua is that the ocean is really dynamic. In this area, the tides are about 1.5 meters, the tidal range, and the waves regularly exceed 4 meters. So you get a lot of wave events, both local storms as well as waves coming up from Antarctic storm events that are basically propagating up here. And as you can see here, it can be a very energetic system. And then another reason why we're interested in it is because it's in what we call an active margin, where we have all this plate tectonics going on. The coastal system offshore is really quite complicated. So shown here in the upper right is a map. Here's the river that's coming into the bay, and then this is what we call the red is what we call the continental shelf. That's kind of the flat area offshore. In the figure below, I have 3 lines of data plotted. These are lines of what we call seismic reflection. This is a tool that looks below. Basically, it sees the seafloor and below. And what you can see is, normally when if you go off the North Carolina coast, it generally gets deeper as you go and then eventually drops really quickly to the deep ocean. As you look here, you see it's getting deeper, and then offshore there's this, what we call an anticline. It's actually a ridge. Okay, this is created because of faults on the seafloor. So there's a ridge that basically acts like a dam for sediment. Sediments are filling up the mid-shelf, and then offshore there's basically this dam that's basically preventing sediments from going further offshore. You'll see that in this line there's a dam, sort of that anticline, and then further to the south there's an anticline, and in between there's a bit of a gap where sediment is kind of leaking through and escaping to the deep sea. So it's a very complex morphological system and related to the geological setting. So we've done a lot of work off of the Waipoua coast. This is just the black lines indicate where seismic reflection data were collected. All these dots represent cores that were obtained on different cruises. And this isn't even including a lot of the cores that we collected on more recent cruises. And then in the orange stars are where we actually deployed tripods on the seafloor that I'm going to show you some data from in a second. Okay, so what's plotted here is the thickness of sediment that's been laying down over the last approximately 10,000 years. Okay, this kind of tells you is where is sediment piling up on what's called the continental shelf. So here's Poverty Bay. This is where the river comes in. And what you can see is a big red spot with a bullseye in it here, another red spot here, and another red spot here. Okay? Those are areas that are basically filling in. They're basins that are created because of basically the tectonics and how they're impacting the system. So we can see that because we have the geology is subsiding in these areas, sediments are sort of filling them in over the last 10,000 years. Since we also have gone out and collected cores and used lead-210 to measure sedimentation rates. And what you can see is generally the sedimentation rates over the last 100 years show a very similar pattern. We see very rapid sedimentation rates here to the south in that one subsiding basin. Also rapid sedimentation rates here to the north, and then also rapid sedimentation rates offshore. So the modern sedimentation is sort of mimicking what's happening over longer term. Shown here is a 3D view of the catchment. Here's where the Raipoa River comes out. And then this is what we call the continental margin offshore. This is the shelf. And then this is the deeper water. And what's essentially happening is sediment's coming out. It's being filling in this one basin, which is blocked by this anticline, and it's filling in this other basin. And some sediment is kind of leaking out through what we call Poverty Gap and accumulating offshore. Now, if we use our accumulation rates from cores, we can actually estimate how much sediment is being stored in different parts of the system. And based on lots of cores, which I won't show you all the data, we can only account for about 44% of all the material that's coming into this system. Okay, what does that mean? It means we are either really bad at math or there's a lot of sediment leaving this area. And it's hopefully the latter, which is that because it's a very dynamic oceanographic system, as I showed you, there's fairly large waves and tides, sediment is being resuspended here and carried off, along the coast and offshore. So a lot is leaving the system. Okay. The last part of the research was trying to understand how sediment was kind of accumulating and how we are creating layers on the continental shelf. I'm not going to get into that too much, but I just wanted to give you a little bit of data to show you a flavor for some of this work. So we had tripods that we deployed both right off of on the shelf right here to the south and basically near Poverty Gap. And I'll show you some data from one of those tripods. We also went out and collected cores 4 times over the course of a year. So first thing I'm going to show you is, let's go back, is data right from this tripod right off of the river mouth. And what's plotted here, it's a lot of data. I'll just quickly describe what it is. The top panel shows you the river discharge. So notice time is on the x-axis, and we basically go from February to January of the next year. And what you see are several different flood events that occurred. Okay, that's what you can see, and you can see water and sediment discharge are plotted. Below that, you actually see a plot of what we call significant wave height. That's the waves that were being felt or seen on the margin. And you can see there's lots of wave activity. Shown here is if we look at the 4, that's 4 meters, about 12-foot high wave, that occurred in March, June, lots in July, August. There tends to be a lot of wave events in their winter, our summer, in this time frame. And then in the bottom panel is the sensor that was deployed on the seafloor that's looking down, and it looks at what we call the backscatter. It basically sends out sound, and based on sound returned to the instrument, we can measure the sediment in the water column. So this is centimeters above the seafloor, And this bright line, the big red line area, is basically where the seafloor is. Okay? And then these sort of flashes of color indicate when lots of sediment got picked up into the water column. And what I want you to note is that there were a couple times when the seafloor basically did a big jump. Okay? That's basically when there was rapid deposition. And if you look carefully at this record, I don't want to spend too much time on this. I just want to highlight that this was essentially the big event. There was one real significant sediment transport event to this shelf, and it was a time when there was a flood coupled to a really high wave event. And it's been suggested in other studies that this is because of the conditions where we have waves offshore and a flood coming into the system, that we actually can, as the river discharges sediment, because there's wave activity, that sediment can basically pile up in the water column and basically can accumulate. And eventually it becomes so dense, the water actually becomes so dense, filled with sediment, that it kind of just flows across the seafloor and can move and deposit fairly quickly out into the ocean. This is something we kind of just recently have discovered in the last couple decades, and it's suggestive that we do have this occurring off of the Waipoa system. Okay, we also went out and collected cores 4 different times. I don't want to spend much time on this, but I just want to show that these are sort of the mean layer thickness, how thick a layer got deposited across the shelf. And what you'll notice is that where we have bright red is the thicker regions, the thicker deposits, and then the lighter reds are where we have thinner deposits. And what's kind of interesting is that this dot pattern doesn't agree with the longer-term accumulation pattern. Okay? Generally, you see deposition to the north, so there is some agreement there. But for the most part, it's a bit more complicated. And what this suggests from the number of sort of observations that we made is that with each event, there's sort of a different story. Some events, they maybe rapidly brought sediment out to the shelf. Some events transported sediment more to the south. Some went more to the north. It's a bit more variable. Each flood and wave event kind of has its own sort of signature. But over time, material gets picked up and resuspended and eventually sort of fills in these lower areas, allowing them to accumulate more rapidly than others and filling up the continental margin. All right, so I'm going to conclude there. You've probably learned enough of sedimentation on coastal systems. Well, the take-home points are here is that there's a lot of variability in what happens once sediment reaches the coast. And this has important implications for biological, geological, and chemical processes. There are some systems like the Albemarle-Pamlico estuarine system where basically the sediment that comes out, it comes into estuaries. Most of it's stored in the estuary, but it's not just that it just sits there forever. It actually goes through quite a lot of dynamic processes driven by the coast, such as hurricanes and other events. Large systems like the Mississippi, the timing of discharge and how that relates to when there's oceanographic conditions is really a big control in when and where sediments end up. And I didn't show you other river systems, but you can take my word for it. And if you want to learn more, just let me know. And then the last system we talked about was the Waipoa. And this is a small mountainous system. And what we showed is that we can release a lot of sediment from these small systems out into the ocean. Some of it might accumulate nearby, but a lot of it's being advected far and wide out into the ocean because of the very dynamic conditions that the ocean experiences. And I'm going to end there, and I'm happy to take any questions.
I got a question about the methods.
Yeah.
For the Mississippi River. On that slide that you had showed like hundreds of those different kinds of cores that you all took. What exactly is the time frame for doing that research as far as like how many cores you get each time you go out there? If it's like 2 trips, if it's like every other day?
All those dots, which I think was like 50, were collected in about a week. Okay. Right? Wow. Sid was on the... So it was a lot of sampling. We actually also had another cruise after a flood in 2011 where we actually went out and did a similar sort of attack on the ocean to collect lots of cores. And yeah, we just, you get in a groove and you work 24 hours and you just collect lots of mud and it's really muddy. Yeah?
Does sediment have any temperature difference?
Does sediment have temperature difference? Well, it really depends on the water that it's in. So if you think about it, really ultimately, just like our soil on land, it's driven by what the air temperature is. The ocean, of course, doesn't always have the same temperature as the air, and that's because it can store, water's really good at storing heat. So it really depends on the water, I would say, and how long it's been in that water will determine the temperature of the sediment.
So sediment coming down from the rivers and whatnot into shallow water, the temperature is not going to affect the shallow water then?
Well, so that's a good question. So one of the things that happens where rivers meet the sea is that the rivers often have their own temperature. They also have low salinity, right? Where river water has low salinity, and often it can have, depending on what time of year, cold or warm water. Salinity and temperature are the two factors that really determine the density of water, which ultimately, the density of water, the fresh water, and as it comes into the ocean, will determine how it basically flows into the ocean. Many of you are probably used to, looking out of the window on the airplane and you see these plumes of sediment, right? That's the basically lower density water that has some sediment in it that's basically floating on top of the ocean. And in fact, it's a really thin layer. It's about usually only on the order of a meter or less thick. And in fact, very little sediment, when you actually have a river that comes out, often kind of people look at the river plume and think, oh, look at where all that sediment is going. That's actually only where a very small, about 10% of the river sediment actually is transported by the surface plume. If you think about it, most sediment is settling constantly, and it's being moved near the bed. And so about 90% of the transport in the ocean is actually in what we call the bottom boundary layer along the seafloor.
Can you talk more about the erosion of land on the south end of
Sure.
here? I was trying to figure out exactly where that was.
Yeah, so that's kind of the marshes at the southern end of Roanoke Island. We've actually done erosion rates throughout Dare County, and in fact, we have data now to do them throughout the state. But those are some of the highest erosion rates that we've seen in North Carolina. Also on the west coast of Roanoke Island, right here at CSI, is actually some of the most rapidly eroding. My feeling is that the real driver for that is that it's a really large fetch system. What I mean by that is it's a really large water body, and any time that you have winds, basically you develop waves that are breaking on the shore. And it doesn't have to be storm conditions. In fact, in that case, those areas, I would imagine it's the summer winds when we have southwest, like just yesterday, or we every now and again have fairly strong southwest winds. That's when you have the entire fetch of Pamlico Sound to build up bigger waves, and those are releasing their energy on the southern end of Roanoke Island. So there's a lot of energy that's basically being released there, and that's driving that shoreline erosion and marsh loss that we see.
So, predicting the future, what happens?
Well, I mean, we're going to continue. There's much concern over sea level rise and its impacts, and certainly there's a lot of reason to be concerned for that. But I think also in our coastal systems, there's a lot of shoreline erosion going on, and that's another big concern because we're losing our wetlands more rapidly because of shoreline erosion than any other process. As far as what that does, I mean, we're just going to continue to lose wetland. There are, for example, some organizations like the Nature Conservancy is trying to investigate how they might mitigate against shoreline erosion. Another bad erosion hotspot is just on the other side of Croatan Sound on Alligator River National Wildlife Refuge. And so they've actually put in some oyster reefs as an effort to try and mitigate shoreline erosion. We are currently working with them. We had an undergraduate student that was looking at how the oyster reefs are basically reducing wave energy and potentially reducing the erosion rate. So we are working with them to try and understand how those things like oyster reefs might be able to sort of naturally protect the system. But they, in addition to providing wave mitigation, they also provide potentially nice habitat for oysters, which is something that our ecosystem has really lost over time for a variety of reasons. But yeah.
What about man-made insertion of barriers? What I have in mind is I was involved many years ago with 5-way pieces of concrete, which they experimented with up in Connecticut. And they dropped them in the water, you dropped the next one, it became an interlocking barrier.
Mm-hmm.
And there was some hope at that time to expand that to other parts of the coastlines to slow down the waves, to keep it simple.
Right, and that's those are things being explored. In fact, you know, I called them oyster reefs, but they're not all oysters. Some of them were essentially marl rock, others. So there are different devices that people have used to try and mitigate against shoreline erosion. Obviously, you know, what a lot of homeowners are doing are putting in bulkheads. What we're, you know, some of our concern is that we want to avoid losing some of the shoreline habitat that's so important. But at the same time, we want to try and preserve the marshes. So there are some challenges there. There are a lot of science going on to try and evaluate what's the best approach. It's also important for people to know that we don't need to put in barriers everywhere. There are some areas that show a chronic history of erosion, and perhaps we want to mitigate against it. But other areas have been accreting or have shown little to no erosions. And in those areas, it's good to preserve the marshes that are there. So I guess what I'm highlighting here is that we kind of have to evaluate this at a location by location basis, and how, if we are going to mitigate, we, you know, hopefully can use methods that will best help the system. There's a lot of debate about that, and the other reality to that is just the cost. We're talking about such a substantial amount of shoreline that, you know, you can only do really small stretches with these reefs just because of the pure cost. So again, that's what's interesting, is to watch what the Nature Conservancy is doing, because they're trying to be proactive, try and protect some of the areas that are worse and test the methods. But it's costly, and it's not easy to get permitting for, oddly enough, because these are sort of new ideas and new approaches. But there are a lot of work going on in different states. Like you mentioned, Connecticut, Virginia's doing a lot. Many of the states are trying to explore approaches and encourage people to do more green approaches for protecting the shoreline, and we'll see moving forward what ends up happening. Yeah.
One of the good things is that we have computers now, so you can start doing modeling much sooner in the days of when you had slide rule, or if you didn't have the ability of the programming.
That's absolutely right. I mean, now what we can do with modeling, we can model as far as the wave climate pretty much, and the hydrodynamics pretty much anywhere. Some of the key controls are having the right input data to do the modeling, but yeah, we certainly are much better equipped than we ever were. I think the harder challenge is the treatment and evaluating the treatment, and those are things that we still have science to do. Yeah.
I hate to stick on the wanches.
No, that's fine. Yeah.
But that's where we are. What's the economic cost of the erosion on the south end of the island?
Good question.
Is there any?
Certainly. Wetlands provide lots of ecosystem services, and there's been many different efforts by different scientists to sort of put a dollar value. How do we quantify those services? There's a lots of different approaches, and I can't speak to that. I'm not an expert in that regard, so I won't even try. But Dr. Andy Keeler here at CSI certainly is familiar with the approaches, and anyway, there's a wealth of research that's going on to try and, you know, make the point that these systems are, and in particular, one of the areas where a lot of this is getting focused on is in the Gulf of Mexico, where people are realizing that those wetlands provide mitigation for storm surge and wave attack. And it's big dollars to do some of these diversion projects to supply sediment. So people are trying to really, how do we value these, not only for the habitat in terms of the biology that lives there, but also for those services that we value in terms of protecting against flooding and so on. So there's a lot of work being done. It's really sophisticated, and I don't want to do it disservice by giving you any wrong information. So I'll leave it at that. But
well let me ask
yeah.
you the comparison. Some show I saw on television, and if it's on television, it must be
true. Yeah, yeah.
Said that in the Gulf of Mexico, they're losing an acre a day.
Yeah.
And I can understand, given the chart you showed with the pipelines and all, the huge economic interest and political interest that would be involved there, totally separate from the environmental interest. Okay, south end of Roanoke Island, south part of Wanchese, doesn't have a similar call to action, shall we say.
Mm-hmm.
Is what you depicted here on this island the result of natural causes, as opposed to in New Orleans or in the Mississippi River Delta, where they were, at least in this program, it was all being attributed to the pipelines, the drillings, the canals, the Army Corps of Engineers, et cetera, et cetera?
I would say in both, I mean, depending on, without trying to get into the argument of whether climate change is natural or anthropogenic, that's a bigger question. But if you just want to talk about maybe the direct effect of humans on the system, I would say most of the changes are probably natural in both systems. In the Gulf of Mexico, if you think about it, you have a really large river system, and you have, because of that system has put in so much sediment into that area, it's causing basically flexure and in subsidence over time, which has basically caused a much higher relative rate of sea level rise. Whereas here, we're in a different geological setting. We do have a pretty high rate of relative sea level rise, but it's not as high. I believe theirs is about 1 centimeter per year, depending on maybe 8 millimeters to centimeter per year. Ours is like 3 to 4 or 5 millimeters per year. So you know, you're talking about a relative sea level rise that's almost double what we're dealing with here. And you're also dealing with really extensive marshes there, because it was this huge river system that over the last few thousand years has shifted its course, and now the river is going, yes, humans are controlling where it's going, and so there's a problem there, but naturally, those areas that are now away from what would be the active source are going to be subsiding, and therefore having a higher rate of sea level rise, relative sea level rise, and having potentially more land loss. So that's sort of a natural process as well. It is overprinted by things like climate change, as well as local pumping, because of groundwater extraction, because of oil extraction, because of human activities offshore, onshore, everywhere. But that would be geologically, if we just look at that, they are two fundamentally different systems, and their problem is certainly a bigger scale problem for largely just from a geological standpoint. Yeah?
Can't you write 2 different logarithms to solve the problems from here and there?
Oh, absolutely. Yeah, I'm not trying to say that ours isn't a problem. They're just different, and they're different scales, and they're certainly different responses. And yeah, there's a bigger economic system there where you've got shipping and all these other factors to consider, cities and so on. That's not to say we shouldn't address the issues that are happening here in North Carolina. They're just different. So, any other questions? All right, well, I'm happy to talk after if you have any questions. Thank you.